So these are the main points of Bohr's atomic model, and using this atomic model, Bohr could overcome the limitations of other atomic models, that is J.J. Thomson's atomic model and Rutherford's atomic model. That was found to be the merits of Bohr's atomic model. He could overcome the limitations of other atomic model. Okay. Now we can study what are the merits and demerits of Bohr's atomic model. First, about the merits of Bohr's atomic model. The first one was that it could explain the stability of the atom. Do you remember what was the limitation of Rutherford's atomic model? Yes, it was Rutherford couldn't explain the stability of the atom. According to Rutherford, electrons are revolving in circular path around the nucleus, but when a charged particle like electron is revolving in a circular path, it will continuously emit its energy and finally it will fall into the nucleus. In such a condition, the atom cannot exist as stable. That means electron and nucleus will collapse with each other. So atom is found to be unstable according to Rutherford's atomic model. So that was the limitation of Rutherford's atomic model. He couldn't explain why the atom is found to be stable. But using this Bohr's atomic model, Niels Bohr could explain how atom is found to be stable. That is, according to Bohr's atomic model, we know that as long as the electron is revolving in a particular orbit, it is not losing its energy. So it will remain in that orbit itself. It is not losing its energy, so it is not collapsing with the nucleus. So atom can exist as stable. Okay. According to Bohr's atomic model, as long as electron is revolving in a particular orbit, it is not losing its energy. As a result, atom can exist as stable. That was the explanation given by Niels Bohr. Then, the second merit of Bohr's atomic model is that using this atomic model, he could explain or he could calculate the energy of an electron present in a particular orbit. We don't want to study the derivation of this equation for calculating the energy of electron, but we should study the formula. How can we calculate the energy of the electron present in a particular orbit? The formula to calculate energy of an electron in a particular orbit is given as En is equal to minus RH into 1 by n square, where n represents the number of orbits. For example, if the electron is present in the first orbit, n will be equal to 1. So we can write E1 is equal to minus RH into 1 by 1 square. And if the electron is present in the second orbit, we can write E2 is equal to minus RH into 1 by 2 square. Okay. So n represents the number of orbit in which the electron is present. And in this equation RH, it is a constant and it is known as Rydberg constant, and its value is equal to minus 2.18 into 10 raised to minus 18 joule. Using this formula, we can calculate the energy of electron present in the first orbit, that is E1 is equal to minus 2.18 into 10 raised to minus 18 into 1 by 1 square, that is 1 itself. That is equal to minus 2.18 into 10 raised to minus 18 joule. Like this, we can calculate the energy of electron present in the second orbit, third orbit, fourth orbit, etc. Okay. So this is the second merit of Bohr's atomic model, that is, we can calculate the energy of electron present in a particular orbit. Now, the third one is that he could explain the line spectrum of hydrogen. Using Bohr's atomic model, he was able to explain how lines are produced in the spectrum of hydrogen when we are passing electric current through the hydrogen gas at low pressures. According to Bohr theory, we know that electron is not emitting energy as long as it is present in a particular orbit, isn't it? But when the atom is subjected to electric discharge, or when the hydrogen gas taken in a discharge tube is subjected to electric discharge, electron is absorbing that energy and jump into a higher energy level, that is known as the excited state. And when this electron is coming back from the excited state, it is emitting the same amount of energy, and this energy is released in the form of radiation. That already we have discussed, isn't it? and this radiation is having a corresponding frequency. It's having a particular frequency depending upon the energy, and according to that it will have a particular wavelength also. This energy is producing some lines in the spectrum of hydrogen. These radiations are appearing as a line in the spectrum of hydrogen. Okay, so that is the explanation given by Niels Bohr. So, when the electrons are jumping back from the higher energy level to the lower energy level, energy is emitting, and these energies are emitting in the form of radiation. So, corresponding to each radiation, there appears a line in the spectrum of hydrogen. Now, the next question before Niels Bohr was that why these many lines are observing in the line spectrum of hydrogen even though hydrogen contains only one electron. It is because when we are taking a small amount of hydrogen gas in a discharge tube, it will contain thousands of hydrogen atoms, and each atom contains one electron each. And each of these electrons will absorb energy and exciting to different higher energy levels. And all these electrons are coming back to the original position either in one jump or in two or more jumps. That means, for example, we can consider the electron jumping from the first energy level to the fourth energy level. So there are different possibilities for the electron to come back to the first energy level. What are the possibilities? The first figure shows that the electron is jumping directly from the fourth energy level to the first energy level. That is, from fourth energy level it is jumping directly to the first energy level. That during that jump it emits some energy, and corresponding to that energy one radiation will be there, and one line also will be produced in the line spectrum of hydrogen. Then what is the next possibility? That electron can jump first to the second energy level, and then from that second energy level it is jumping into the first energy level. There is a possibility for that, isn't it? Without jumping from the fourth to first it is jumping in from the fourth energy level to the second energy level. From there it is jumping to the first energy level. So here occurs two jumps. So corresponding to that we will get two lines in the spectrum. Then what is the third possibility? The electron is jumping from the fourth energy level to the third energy level first. Then from the third energy level it is jumping directly to the first energy level. Here also there occurs two jumps, but the energy emitted in these two jumps will be different. So corresponding to that we will get two different lines in the spectrum of hydrogen. Then what is the fourth possibility? The electron is first jumping from the fourth energy level to the third energy level, then from that it is jumping into the second energy level, then it is jumping to the first energy level. So according to that we will get different lines. Here there are three jumps, and during these three jumps the electron is emitting energy in the form of radiation, and corresponding to this radiation we will get three different lines in the spectrum of hydrogen. Okay, so all these are the possibility for the electrons. So depending upon the jumps we will get different lines in the spectrum of hydrogen. So there occurs many number of lines in the spectrum of hydrogen. Okay, now the line which is produced when an electron is jumping from any of the higher energy level to the first energy level, that line belonging to the Lyman series. The line corresponding to the jump from any of the higher energy level to the first energy level, that corresponding to the Lyman series. Like that, if an electron is jumping from any of the higher energy level to the second energy level, that line we are getting in the Balmer series. Then if the electron is jumping from any of the higher energy level to the third energy level, that line corresponds to Paschen series. And if the electron is jumping from any of the higher energy level to the fourth energy level, that line we will get in the Brackett series. And if the electron is jumping to fifth energy level from higher energy level, that line we are getting in the Pfund series. Okay, so according to this jump of electron we will get different lines in the spectrum of hydrogen. Okay, so these are the merits of Bohr's atomic model of atom. Next, we can study about the limitations or demerits of Bohr's atomic model. Even though Bohr was able to explain the line spectra produced by hydrogen atom, he was not able to explain the line spectra produced by multi-electron atoms. That means atom containing more than one electron. Then the second limitation was that he was unable to explain the splitting of lines in presence of magnetic field. That means when we are applying a magnetic field, the lines are again splitting into still smaller lines. That effect is known as Seemann effect. That was not explained by Niels Bohr. Like that, when we are applying an electric field in atoms, these lines are again splitting into still smaller lines. That was also not explained by Niels Bohr, and that effect is known as Stark effect. Like that, he was not able to explain the three-dimensional model of atom, and different atoms are having different shapes, or different molecules are exhibiting different shapes. Why these molecules are exhibiting different shapes? That was not able to explain by Niels Bohr. Then the sixth point is that he was not able to explain the de Broglie's concept of dual nature of matter and Heisenberg's uncertainty principle. These things we will discuss later. Okay. So these are the limitations of Bohr's atomic model. I think it is clear for all of you.